All right, so the first set of vector problems that we're going to work this semester are actually kinematics problems. And so what kinematics is it's the branch of mechanics that's concerned with describing an object's motion. And so let's just start with basically just laying out the basics, mostly terminology, of how we describe an object's motion. So the first thing we might want to ask is, where is an object located? And that's going to be the position vector. And so the position vector, which we're usually going to denote R, is going to tell you something about where an object is located, what's its x-coordinate, what's its y-coordinate, what's its z-coordinate. It's a vector that runs from the origin to the object's location. So obviously, an object can be in the same place, but if you pick a different origin for your coordinate system, then it'll be described by a different position vector. Position has dimensions of length, so the units that we're going to need when we describe position vector, our SI units, are going to end up being meters. So here's a situation where initially, here's my object, and you can see I've got my initial position vector drawn out from the origin. Here is some final position vector. And so all I know is that my object was here at some initial point in time and was here at some final point in time. So the other question that I can ask is, well, how did my object's position change? And that's described by the displacement. So the displacement is just the change in, so capital delta, the way we often use it in scientific classes, just means the change in position. It's another way of saying the final position vector minus the initial position vector. And so notice this is a vector subtraction problem. And so I'm going to draw a vector that runs from the tip of my initial position vector to the tip of my final position vector. That's another way of saying it's a vector that runs from where my object is located initially to where my object is located at the end point. So all this makes perfect sense in terms of what we know about graphically how you draw in vector subtraction. And again, since I'm subtracting two things that have dimensions of length, the displacement vector also has dimensions of length. Now, a different question that I can ask is to describe how far an object has traveled. So again, let's say I've got an object that its initial position was here and its final position was there. Here's still the displacement. But how far the object traveled in getting from here to there now cares about the path that the object took. Right? It could have gone straight there, so walk straight along the displacement vector. Or it could have gone any of a number of different paths to get from this initial point to this final point. So how far an object has traveled is asking about the distance. And so distance is a scalar quantity. Again, it doesn't care that your direction as you're walking was downwards and then pointing mostly to the left and then coming back up, right? It doesn't care about all those details. It just basically says, every time you take a step, add it up. Let me know how far you actually walked in going from this point to this point. So displacement and distance, those are two things that we'll sort of use interchangeably, but they're fundamentally different things, right? One of them is a scalar. The other one is a vector. And so we'll have to sort of keep in our mind when we're talking about which one and what difference that makes. Again, distance just has dimensions of length, so the SI units that we'll use for dimensions will also be meters. All right. Again, displacement only cares about where you start and where you finish. Distance cares about how you got from where you started to where you finished. So one of the interesting things is, and we'll see this consistently when we talk about our average kinematical quantities, is that the displacement vector basically doesn't care at all about what you do between the instant it starts and the instant you stop. And all those details are irrelevant as far as the displacement vector is concerned. Distance does care about them. So you need to keep track of those details in thinking about the distance. You don't need to keep track of any of those details when thinking about the displacement. Next question, or set of questions that we might ask, is how do we describe how fast an object is moving? And then how do we describe in what direction an object is moving? And again, here are two quantities that are fairly well related and often used interchangeably, but one of them is a scalar quantity and one of them is a vector quantity. So speed is how fast an object is moving. And again, speed is a scalar. It has dimensions of length per time. So the units we're going to use for speed will be meters per second. That's our SI unit for speed. Velocity is how fast and in what direction an object is moving. So notice here we don't have a vector symbol. Speed's a scalar. Here we do have a vector symbol. So we're going to use what the velocity is at any instant in time, it's the vector whose magnitude is equal to the speed of the object and points in the direction that the object is traveling. So if, let's say at this initial point in time, my object was located there, there's the position vector, but it was traveling at a certain speed that's denoted by this length, right? So the magnitude of that is going to tell you what the speed is. The magnitude of that velocity vector will tell you what the speed is, and it happened to be traveling in this direction. At some final position vector, well, now it's traveling in this direction. At some final instant in time, it's got a final position vector because it was traveling in this direction with a certain speed. You notice that the magnitude of this velocity vector is shorter than the magnitude of that. It's roughly half. So that tells you that your object was traveling roughly twice as fast initially because it's twice as large a vector. Its magnitude is basically twice as long. Again, as with speed, velocity has dimensions of length per time, and so the SI units we'll use for that will also be meters per second. Well, what if we're interested in how an object's velocity is changing? So that's the acceleration. The acceleration tells you how an object's velocity is changing. It's a vector with a magnitude equal to the rate of change of the velocity vector with respect to time. And so when we sort of see these definitions in terms of the calculus, this phrasing will probably make a little bit more sense, but the rate of change of the velocity vector with respect to time is just another way of saying I want to take a derivative with respect to time of the velocity vector. Notice that there are three ways that you can change a velocity vector. You can speed up, magnitude gets longer. You can slow down, magnitude gets smaller. Or you can change directions. So what the acceleration will tell you about is any of these things. And so if your object is speeding up, then it's accelerating. If it's slowing down, then it's accelerating. If it's changing directions, then it's accelerating. So you need an acceleration for any of these three things to occur. And that's at odds with the words that we often use to talk about speeding up, slowing down, those types of things. So we'll be very clear about that in class, that all of these are ways for an object to accelerate. So since we're interested in how the velocity is changing with respect to time, that means the dimensions here are going to be length per time, the dimensions of velocity, per time again. So this is length per time squared. So the units for acceleration in SI are meters per second squared. And so these are basically the key ideas that we're going to keep track of in terms of thinking about our kinematics problems. So position, displacement, distance, speed, velocity, and acceleration. And so understanding how these things are the same and how they're different, all that's going to be important in terms of figuring out what's going on kinematically.